Hi. Excuse me. This video has the solutions for your Chapter 6 Fundamental Theorem problems. There's a few different kinds of problems here, so what I'm going to do is give a little explanation for each section, and then I'll go through the problems pretty quickly after that explanation. So for the first 5 here, these are really fundamental theorem type 1 problems, and let's see if this pen's going to work okay for me. It will work all right. And so these are problems where we're taking the derivative of an area function, and they're pretty straightforward, or this first one at least is pretty straightforward, and then the next few have some little tricks in them. So let me just give you kind of a general explanation of what's going on here. We know that the fundamental theorem of calculus, part 1, says that if you have an integral, that's what we call these things now, that's our new name for these, an integral from a number, any number, up to x of some function, and we take the derivative of that, we just get the function. Notice that this is f of x, not f of t, like the x is sort of dropping in here, right? This is just, the t is really just a placeholder. Now, things get a little trickier if this thing up here is not just a function of x. So, for example, what about if we had d dx to something like some other function of x here, like 2x or x squared or something like that, of f of t. And I should say this, let's call this, let me call this g of x, right? It's not the same function. It certainly doesn't have to be the same function. Then what's that equal to? Well, if we do a little substitution here, and we let, let's say, u equal g of x, then here we could turn this problem into, this would be now the integral from a to u of f of t dt. But we can't, if the variable here now is u instead of x, then we'd have to take the derivative with respect to u, right? It'd have to be d du. And if we want it to be d dx, then I'd have to multiply here by du dx, right? Because then the u's would cancel out, and then I'd get d dx. So what this basically means is that we're looking at a chain rule problem here, which shouldn't be any big surprise. It's like this thing is the what's inside. So here, that means we would end up with f of u, right, instead of f of x, times du dx. Right? So we just have to multiply that by the derivative of whatever function we're dropping in there. That's all. So that's pretty easy to do, and we'll see that in an example in a minute. There's another situation, or another two, that we have to talk about. What if the things are the wrong way around? Then what do we do? Well, we know that if it's a to x, then it's just f of x. And we also know that if we throw a negative sign out in front, we can switch these. We've already seen this earlier in our area problems. So that's all that's necessary to do that. So it would just be negative f of x there. And then last, we have the kind of tricky case where we've got things at the bottom and the top that are both functions of x. Like, let's call this one down here g of x and h of x, f of t dt. Now, if we imagine here that we can break this up by our area rules, I'm going to draw a picture that doesn't necessarily have to be the picture of this, but it will suffice here. So let's say like this is our g of x value, this is our h of x value, and then we pick some number in the middle, let's say a. Then we could break this area up into the area from a to h of x of f of t dt, and then here I would have this area, and that would be plus the area from g of x to a, right? Here to here plus here to here, f of t dt. And we're taking the derivative of this whole thing. So by combining the rules that we have above, by combining this idea here, this chain rule idea, and this idea of being able to switch them, this turns into f of h of x times the derivative of the h of x function, right? That's just this rule. And then here, these are the wrong way around, so that would just be minus f of g of x times the derivative of the g function. And I could have just called that h prime of x, right? That would have been maybe easier to do that, right? Okay, so that's as complicated as this can get. And we're using basic area rules here, so let's see what that looks like when we do the actual problems here. So number 1, we did this in class, but I'll put it here in the video just so we have them all. We have, what's the derivative of the integral from 3 to x t squared dt. The derivative and the integral cancel each other out, and the x drops in. It's just x squared. That's the simplest kind. And notice it does not matter what this number is. That number, it does not matter. If you think about why it doesn't matter, well, you should think about why it doesn't matter. It doesn't matter because the rate of change of the area function doesn't matter where you start counting area at. We're really interested in the rate of change is like what's happening at the leading edge of the area function. So as long as that's a number, it just goes away. It's like a constant. Number 2, we have from x to 2, tangent t dt. Now this looks just like this one, except it's the wrong way around, so that just means that we have to put a negative sign to switch those. That's going to be negative tangent of x. And again, that could have been any number. Number 3, we have d dx of, from 1 to 2, 3 natural log t dt. So this will drop in here. So that's 3 natural log of 2x. But since it wasn't just an x there, like I was showing you a minute ago, we have to multiply by the derivative of what's up there, like the chain rule. So you can write that, that's 6 natural log of 2x. Number 4, now we have a function of x at the top and the bottom. And let's see, that's of t squared. So that's an example where this will drop in. So that's x squared squared times the derivative of what's inside minus x squared times the derivative of what's inside, but that's just an x, so that's just 1, right? You can write that there, I suppose, if you want. So that would be what, 2x to the 5th minus x squared. And please look back at the explanation for what to do when those are. You should rewind that if you're unclear about how that worked. And then last one, we've got d dx, the integral from x squared to sine x of 1 over t squared plus 1. So this drops in first. We have 1 over sine squared x plus 1 times the derivative of what's inside, is cosine x, minus, that drops in here, 1 over x squared squared plus 1 times the derivative of that. That's how you do those. I don't think I've ever seen a College Board problem that was quite as not that that's very hard to do, but usually they throw in every once in a while one where you have a number up to like 2x, more like number 3. Okay? These 6 through 10, a little more straightforward maybe. We're just finding the general antiderivative, which means that it's going to be some f of x plus c. The general means it could be any of those antiderivatives, so we'll put the plus c on there to represent that generality. So here, maybe I'll just do these right on this sheet here, because these are pretty quick. What's the antiderivative of x squared? Well, it would be x cubed over 3 plus c. Number 2, the antiderivative of cosine is sine. So the antiderivative would be sine x plus c. And then you can always check by taking the derivative of, I forgot the 2. Take the derivative of this. The derivative of 2 sine x would be 2 cosine x. The derivative of c, constant, would be 0. It gets us back to here. The derivative of 5 over x, maybe that's better to think of that as 5 times 1 over x. Right? Because we know the antiderivative of 1 over x is the natural log function, so that's just 5 natural log x plus c. Now, these, we have to recognize these things. 1 over 1 plus x squared, that is a derivative that we should recognize. That's the derivative of the tangent inverse function. And here, that's negative 6 times e to the x. The antiderivative of e to the x is e to the x. So that's all we have to do there. We don't have any point on the antiderivative, so we can't solve for c here. We're just finding the general antiderivative. Here, we're now evaluating definite integrals. So this is Fundamental Theorem of Calculus, Part 2. We know that we evaluate these by finding the antiderivative and then plugging in the so-called limits of integration. Top first, minus bottom, and we can interpret this if we want to. This is the area under the x squared curve from 1 to 3. It's exactly 26 over 3. Here, the antiderivative of the cosine function is the sine function from negative pi over 2 to pi over 2. So sine, that's sine of pi over 2 minus the sine of negative pi over 2. Sine of pi over 2 is 1 minus the sine of negative pi over 2 is negative 1. That's equal to 2. And that shouldn't be a big surprise because that's the area under the cosine curve, and the cosine curve looks like this, and that's negative pi over 2 there. So that area should be the same as the first bump of the sine curve, which we did in class. So no big surprise there. Here, the antiderivative of 1 over x is natural log x. So 3 over x is just 3 natural log x. And I'll show you here, if you have a constant like that, you can put it outside just because of the distributive properties of multiplication. You can leave it in there if you want. You can pull it outside if you want. You will get the right answer either way. You should justify that to yourself. So that's three. Here we've got a reverse power rule, so let's see if we can figure that out. And we've got x to the 3/2, the antiderivative, the exponent will go up 1, and then we have to divide by the new exponent. Now, I could put a 2/5 here, but it's going to be, I think, a little easier to do the math if I put the 2/5 out here, just like I put the 3 out here. It's up to you, but I think it's easier to manage if you put it out here. Then we have 2/5 times 9 to the 5/2 minus 4 to the 5/2. That's maybe a little bit much without a calculator. Let's see if we can do that. If you do this part first, a 2 on the bottom means square root. So the square root of 9 is 3. To the 5th power is 243. And then here, 4, the square root of 4 is 2. 2 to the 5th is 32. And that gives us, what? 211 times 2 over 5. Here, we've got, we should recognize this. That's the derivative of the sine inverse function from 0.5, which is 1/2, to 1. So that's the sine inverse of 1 minus the sine inverse of 1/2. And we have to be able to do things like this comfortably without a calculator. The sine inverse of 1 is pi over 2. The sine inverse of 1/2 is pi over 6. So pi over 2 is the same as 3 pi over 6 minus pi over 6 would be 2 pi over 6 or pi over 3. All right. Here, these are sometimes called initial value problems because we have a derivative here given, and we've also got a value on the function, which means we can solve for c. So these are a lot like these problems. We're finding an antiderivative, but we've also got a point that we can plug in and then solve for c. I think I might need a little bit more room for these, so I'll do them on a separate sheet here. So number 16, we have f prime of x is equal to x cubed plus 2, and f of 1 is equal to 2. If the derivative is x cubed plus 2, the antiderivative is x to the 4th over 4 plus 2x plus c. Right? Just take the antiderivatives piece by piece. You can check that. Make sure, just kind of mentally take the derivative of this. Make sure you get that. And then we can plug in the point that we have. So 2 is equal to 1/4 plus 2 times 1 is 2 plus c. So c is equal to -1/4. Now that's not the answer. The answer is f of x is equal to x to the 4th over 4 plus 2x minus 1/4. So it may be interesting to note here that the solution to one of these problems is a function, right? Here's a derivative and a point. The solution to this initial value problem is the function that has those two properties. Sometimes we feel like, I've had a lot of students in the past who feel like once you get the c equals that you're done, but you have to write that final answer. Okay? Number 17, we have the derivative of some function is equal to sine x, and f of pi over 3 is equal to 1. So the antiderivative of the sine function is negative cosine plus c, and then we plug in the point that we're given here. 1 is equal to negative cosine of pi over 3 plus c. So 1 is equal to negative, the cosine of pi over 3 is 1/2 plus c, so c is equal to 3/2. And that means that f of x is equal to negative cosine x plus 3/2. Right, so this is the special function that has this derivative and also goes through this point. Number 18, and f prime of x is equal to 3 over x, and f of e is equal to 2. So the antiderivative of this is 3 natural log x plus c. We've got this point, 2 equals 3 natural log e plus c. Natural log of e is 1. 2 equals 3 plus c, so c is equal to -1. And that means the function we're looking for is 3 natural log x minus 1. Number 19, if f prime of x, it says the cube root of x. I'm going to write it as x to the 1/3 because that's more calculus friendly. And f of 8 is equal to 1. The antiderivative of that, we bump the exponent up 1 and then divide by the new exponent. You can check that real quick, make sure that's the right derivative. Plus c. Then we plug in our point. So 1 is equal to 3/4 times 8 to the 4/3 plus c. That's the cube root of 8, which is 2 to the 4th is 16. Oh, 16 divided by 4 is 4, times 3 is 12. So c is -11. And the function we're looking for is f of x is equal to 3/4 x to the 4/3 minus 11. And again, not to be repetitive, this is the special function that satisfies these two conditions. Its derivative is this, and it goes through this point. The last one in this group, number 20, we've got, let's see, derivative is -2 over the square root of 1 minus x squared, and f of 1 is equal to 2. Now that's the, you can deal with this two different ways. You can take the negative 2 out to the front and say that's negative 2 times 1 over that. That would be the sine inverse function. Or you could just take the 2 out and then say it's cosine inverse. So either one of those will work. I'm going to do it this way. And then plugging in the point here, we got 2 is equal to negative 2 times the sine inverse of 1 plus c. That's 2 equals negative 2. The sine inverse of 1 is pi over 2 plus c. So 2 is equal to negative pi plus c, or c is equal to 2 plus pi. So the original function that we're looking for is negative 2 times the sine inverse of x plus 2 plus pi. And again, that is the special function that goes through, that has this derivative and goes through that point. All right. Next group, we have, this is an interesting fundamental theorem part 2 kind of problem that we're going to see a lot of. This sort of thing will be very important to us, especially when these derivatives are contextualized in some kind of problem where the derivative means something at some kind of rate. But for now, these are just sort of abstract problems. But we do know from, in these we're supposed to find f of 1. So here, I know from fundamental theorem part 2 that this is equal to f of 2 minus f of 1, right? The antiderivative of f prime is just f, right? And here that's equal to 5. So f of 2, we're given that that's 3. So 3 minus f of 1 is equal to 5. So of course f of 1 then would have to be equal to negative 2. Here we have f of 1 minus f of 2 equals 5. And switching those, you see, you might think that that's going to give us a different value for this, and it does. So f of 1 minus f of 2 is 3. So that time f of 1 is equal to 8. Here would be so f of 1 minus f of 0 would be equal to 5, and f of 0 is negative 7. So that'd be plus 7 if I subtract that, so f of 1 is negative 2 again. Here, f of 2 minus f of negative 1 is equal to 5. And f of 2 is equal to 1, and f of x is even. Alright, got to think about that for a second. What does it mean for a function to be even? For a function to be even, that means that if f of 1 and f of negative 1, if you've got an even function, what's the relationship between those? And pause and think about that for a second. If you're not sure, make a quick sketch. If a function is even, then whatever it does on one side, it does a mirror image on the other side. So that means whatever f of 1 is, f of negative 1 is the same. So that means here we have, I know what f of 2 is, it's 1, minus f of 1 and f of negative 1 are the same. So f of 1 would be negative 4. A little tricky. And here, same kind of idea, except we've got an odd function here. So let's see. It means that f of 2 minus f of negative 1 is equal to 5. So what does it mean? We need to know about f of negative 1. Can we pause for a second again? They're not the same now. That's what happens when they're even. If it's odd, then we know that whatever happens on this side happens exactly the other way. So whatever f of 1 is, f of negative 1 is the opposite. So these are opposites here. So let's see what we can do with that. So 8 minus negative f of 1, right, I'm making that substitution there, is equal to 5. So that means that f of 1 is negative 3. Okay? And here, a little bit different. These, we're not taking, these look kind of like numbers 1 through 5, but we're not taking the derivative of these. So, can you do fundamental theorem of calculus part 2 on these? The answer is yes, you can. So, what is the antiderivative of the t squared? Antiderivative of t squared is t cubed over 3 from 1 to x. So that's just x cubed over 3 minus 1/3. And here we have the antiderivative of 1 over 1 plus t squared. That's tangent inverse. T from negative 5 to x. So, just like fundamental theorem part 2, that's tangent inverse of x minus tangent inverse of negative 5. Every once in a while, the tangent inverse function is an odd function, and that means that you could pull this negative sign out to the front, just like this. This negative sign could come out. Every once in a while, College Board likes to get cute and see if you know things like that. So just watch out. You never know when you might see something like that. Those two things are equal. I would be perfectly happy with that answer, but it is equivalent to that. And finally, these are really just like, I'm not sure why I decided to put these on here because they're exactly like these, but I'll do them for you anyway. And I'll take a little bit more room to do them. So number 28, we have f prime of x is equal to x squared, and f of 2 is equal to 1. Again, this is exactly the same kind of problems as 16 through 20. The antiderivative of that is x cubed over 3 plus c. Plug in our value. C is equal to negative 5/3. So the function we're looking for is x cubed over 3 minus 5/3. Number 29, we have f prime of x is equal to 6 over x, which is the same as 6 times 1 over x, and f of e is equal to negative 6. So the antiderivative of that is just 6 times natural log x plus c, plugging in the one point that we know, gives us c is equal to negative 12. So the function we're looking for is 6 natural log x minus 12. And the last one. Function is 4 over the square root of 1 minus x squared, and f of 1/2 is equal to 1. Antiderivative of this is 4 times the sine inverse of x plus c. Plug in the point that we have here. It's 1 equals 4 times the sine inverse of 1/2 plus c. Sine inverse of 1/2, that's pi over 6, times 4 is 2 pi over 3, plus c. So c is 1 minus 2 pi over 3. And the function we're looking for is f of x is equal to 4 times, sorry, I don't know why I put those parentheses there, that's not necessary, plus 1 minus 2 pi over 3. There you go.